Here's problem 23(9). If A is equal to 3 millimeters, B is equal to 4 millimeters, Q1 is equal to 60 nanocoulombs, Q2 is 80 nanocoulombs, and little q is 32 nanocoulombs in the figure, what is the magnitude of the total electric force on little q? So we have Q1, and it's positive charge, and we have Q2, and it's a positive charge as well, and little q, which is a positive charge. And even though this is a two-dimensional problem, we're going to approach it in the similar way as we did with one-dimensional problems. In other words, we're going to find the net force, find them as vectors, and then add those vectors together using vector methods. So in this case, we have Q1 and little q, and they're separated by a distance along their line of action. There will be a force of repulsion between these two positive charges going down like this, and let's call that F1. The angle of that force, let's call it theta, is actually going to be the same angle as this angle right here, theta here. And then if I look at Q2 and little q, there's going to be a force along their line of action, and that's going to be going up like this. Let's call that F2. And the angle of that actually is going to be the same angle theta. It's the same triangle. So that's going to be going up like that with the same angle theta. So we want to find the magnitude of these two forces, turn them into vectors, and then add them together. Now when looking at our triangle with our A and our B, we have A is 3 millimeters, B is 4 millimeters. Our hypotenuse will be equal to 5 millimeters. So this distance between these charges will be 5 millimeters according to the 3, 4, 5 triangle. And we could verify that using Pythagorean theorem, but we know that that should be a 3, 4, 5 triangle. Okay, so our force 1 is going to be equal to K Q1 little q over the distance between them squared. That's going to be 9 times 10 to the 9 times Q1, which is 60 nanocoulombs, times little q, which is 32 nanocoulombs, all over the distance between them, which is 5 millimeters, squared. Alright, so 10 to the 9 and 1 to the 10 to the minus 9's cancel out. And this is equal to 9 times 6 times 32 times 10 to the minus 8 all over 5 times 5 times 10 to the minus 6. And what is that? 0.691 newtons. Alright, so that's the magnitude of the first force. Let's find the other force, F2, and that's going to equal K Q2 little q over the distance between them squared. And that's going to be 9 times 10 to the 9 times 80 nanocoulombs times 32 nanocoulombs over the distance between them, which is 5 millimeters as well, and we'll square that. So again, 10 to the 9, 10 to the minus 9 cancel out, and this is equal to 9 times 8 times 32 times 10 to the minus 8 over 5 times 5 times 10 to the minus 6. And what is that? 0.922 newtons. Alright, so that's the magnitude of the second force. And if we were to break these up into components, we would say that force number 1, which is going down in the negative y direction by the positive x direction, would be equal to 0.691 cosine theta I. This is going to be our vector, minus 0.691 sine theta j. Those are our two components, positive x, negative y. And we could figure out theta, but if we look at the triangle, the cosine of theta is going to be the adjacent side over the hypotenuse. Adjacent side is 4 millimeters, the hypotenuse is 5 millimeters. So the cosine of theta is going to be 4/5. And for that matter, for our 3, 4, 5 triangle, the sine of theta is going to be 3/5. So this is going to be equal to 0.691 times 4/5 I minus 0.691 times 3/5 j. So 0.691 times 0.8 is 0.553 I minus, and 0.691 times 0.6 is 0.415 J newtons. All right, so that's our F1. We're going to need another screen for this problem. Our F2 as a vector is going to equal 0.922 cosine theta I plus 0.922 sine theta j, because they're both positive components. And that's going to be 0.922 times 4/5 I plus 0.922 times 3/5 j. 0.922 times 0.8 is 0.738. And 0.922 times 0.6 is 0.553. All right, so that's our second vector force, F2. We wish to add this to that first vector force. So we have that our net force, which is F1 plus F2, is going to equal 0.553 plus 0.738 I plus 0.553 minus 0.415 J. And that's going to equal what? 1.29 I plus 0.138 J. That's our resultant net force on little q. Well, we want to find the magnitude of that force. So these two components are perpendicular to each other. This is newtons. They're perpendicular to each other, so the magnitude of this force is going to equal 1.29 squared plus 0.138 squared, square root. And what is that? .297, so we'll say 1.30 newtons. So the magnitude of the force on little q is 1.30 newtons. So that's our answer.